Okay, now let us continue with that derivation for lumped heat transfer approach or lumped capacitance approach. Okay, so we found out an equation for the temperature distribution, that is theta over theta I, right, is equal to e raised to minus pi, that is the Biot number, times the Fourier number. Okay, this is the equation for temperature distribution in the case of unsteady state heat transfer. Okay, now let us now find out, and later on we will discuss about the significance of the Biot number. Okay, and now let us discuss about the heat transfer rate. So the rate of heat transfer Q will be equal to what? Let's check it out. Integral 0 to t Q dt, because this is time dependent and this is the Q is the rate of heat transfer. So capital Q will be equal to integral 0 to t Q dt, right? And we have seen that will be equal to H as integral of 0 to t theta dt. Now what is the value of this theta? That is what is, so this equation is obtained from the previous slides or previous video. So Q is equal to HAS times integral of 0 to t theta dt. And we know that theta, what is the value of theta? The theta was equal to theta, we know that the theta value of theta is equal to theta I times e raised to, so if I write it like that, e raised to minus HAS over OVC times T. Okay, so that is the value of theta. So if you, now we have to integrate this thing and find out the value of theta. Okay, the value of Q. Okay, so Q will be equal to HAS times theta I times integral of 0 to t e to the power minus HAS over rho Vc times t, okay, dt. Now to integrate this thing, let us see what is the general equation, general formula 0 to x. So or if you don't, if you just keep integral of, does not give the limits for the time being, so integral of e raised to minus ax, e raised to minus ax. So what is that? The integral of e raised to minus ax is actually equal to 1 by a, so you have a negative symbol there, 1 by a e raised to minus ax. This is the integral. So if we apply that equation here, this will be equal to what? HAS times theta I, and you get 1 by negative of, so you have the negative sign there, so let us keep the negative sign outside. You have this thing, and A comes as denominator, so HAS will come here times OVC integral of 0 to t, sorry, not integral, limits, right, exponential of, so we can see that this is actually equal to OVC times e to the power, or e to the power negative HAS times t over OVC. Okay, for the limits in between the limits 0 to t. Okay, now if we evaluate this thing, we'll get Q will be equal to the rate of heat transfer. Q, or the total heat transfer, will be equal to what? At H and H will get cancelled, so this is rho Vc, negative of rho Vc theta I times e raised to next thing. So e raised to that power. The first one is to e raised to minus h, the upper limit is HAST over rho VC itself, and the bottom one is e raised to 1. So this is minus 1. Okay, e raised to 0, so that you will get this minus 1. So if you take the negative sign inside this thing, so you get this is rho VC times theta I 1 minus e to the power negative HAS times T over rho VC. Okay, so this is what we get. So e to the 1. Now we have seen that this value is actually HAS over rho VC is actually 1 over the time constant, thermal time constant. So this is actually equal to rho VC times theta I times 1 minus e to the power minus T over tau Th. Okay, so this is the rate of heat transfer as far as the lumped capacitance method is concerned. Okay, now going back to the other one, let us see what is the importance of Biot number. So we have seen that Biot number is equal to HLC over K, where this LC is actually the characteristic length. Okay, now what is this characteristic length in the case of a plane wall? In the case of a plane wall, the characteristic length is the L itself. Okay, it's the length itself. Now when we are talking about the length, if you consider a plane wall like this, let us say I have a plane wall, and if we take the center, if there is some kind of heat generation of something, so if this total distance is 2L, then half of that is actually equal to the characteristic length. The characteristic length is where you have a definite change. Okay, here you get the temperature profile to be like the temperature, there is a heat transfer from here to here and from here to here, right? Because this is the heated, this is the material that is the heated one, so there is a temperature towards both sides, a heat transfer to both sides, and so this side will be equal to, this length is actually equal to L, which means that the characteristic length is actually L. Now in the case of so for a rectangular plate, the characteristic length is actually L. So L is LC is actually equal to L for a rectangular plate, for a plate, flat plate. Okay. Now then we have LC is equal to the radius by 2 for a long cylinder. Long cylinder. And then LC, the characteristic length, is actually equal to R over 3 for a sphere. Now if it is a cube, then LC is L over 6, where L is the side. Cube. L is the side, a side of the cube. Okay. So you can see that L is here, L is the side. So the first one is actually for this one. Okay. Now let us see what is the significance of Biot number. So significance of Biot number. Okay. So what is this Biot number? This is HL by K. So HL by K, what is HL by K? So Biot number can be written in a different form also, that is Biot number is actually equal to LC by K divided by 1 by H. Now what is this? L by K is actually the conductive resistance. And 1 by H is actually convective resistance. Okay, so L by K is conductive resistance and 1 by H is convective resistance. So if you write the Biot number, so you can write it as Biot number is equal to the conductive resistance over the convective resistance. So what does this mean? What is this conductive resistance and what is convective resistance? So if you take a material, some metal block or something like that, we know that there is a heat transfer inside the block. From the center to the surface there is a heat transfer inside the block. Now when the heat transfer, mostly if it is a solid, this heat transfer is conductive heat transfer. Now if the conductive resistance is actually high, in this case, if the conductive resistance is high, you can see that there will be a temperature gradient. I'll show you another picture for that. And okay, there will be a temperature gradient. And then convective resistance is actually the resistance to heat flow from this metal or the solid to the surroundings. So when the convective resistance is high, what happens? So when the convective resistance is high, the heat transfer to the surroundings is reduced. Okay, and when the conductive resistance is high, the heat transfer inside the body is reduced, which means that there will be a temperature gradient inside the body. So if I actually bring in a picture and I'll explain that. Once again, I've used this picture from the textbook in Crocodile. Okay, so if I open that, it's taking some time. Okay, place it here. Okay, so you can see this when the Biot number is actually, so this is a picture for Biot number. So we have seen the definition of Biot number. So Biot number is actually resistance, right? Conductive resistance over convective resistance. Conductive resistance over convective resistance. Conductive resistance. Okay. Now, when the conductive resistance is very small, it means that conduction is almost infinity. There is pure conduction and there is no resistance to the heat flow. So when the conductive resistance is very small, means that the temperature gradient is not present. That is what we saw in the previous lesson, or in the previous video, that when the conductive resistance is very small, we saw that the temperature gradient is not, present. Okay, so there should be a small temperature gradient, otherwise heat transfer is not going to happen, but still it is very small. Okay, so when the numerator is small and the denominator is large, means that the Biot number will be less than 1, much less than 1. Okay, when the Biot number is much less than 1. And this is the case when we can actually use the lumped heat transfer approach, because in the initial introduction to the lumped heat transfer approach itself, I have told that the Biot number, the lumped heat transfer approach can be used when the temperature gradient is actually not present, okay, or the temperature gradient is very small. So when the temperature gradient is actually very small, the lumped capacitance method can be used. And now we have to get a quantitative idea of how small the temperature gradient should be. That is given by the Biot number. Okay, so if the Biot number is actually very small, that is much less than 1. So to be precise, the Biot number is approximately equal to, if you take the Biot number, approximately equal to 0.1 or lesser. In that, so lesser than 0.1, in that case we can use the lumped heat transfer approach, which means that we take this, in that case we take this metal as a whole and as a lump, and we assume that the temperature gradient inside that metal is actually, or metal or any substance, is actually very small. Now if you look at this picture, you can see when the Biot number is very small, the temperature gradient, the difference between temperature TS1 and TS2 is very small. The line is almost parallel, but there is a small difference, a small inclination that should be there, otherwise there won't be heat transfer. And when it is equal to 1, see that the temperature gradient is much steeper. When it is greater than 1, the temperature gradient is even more steeper. Okay, which means that, what can you say, now the infinity temperature of the surroundings is given as T infinity. You can see that at Ts2, the surface, from that there is a line coming down like this. T infinite, from that there is a line coming down like that, and that will almost reach the T infinity. It is going down till T infinity. That is the reason why we have a convective heat transfer. We have convective heat transfer to the surroundings, Ts to T infinity. So Ts2 is actually much greater than T infinity, and then Ts3, S2 in this case is also much greater than T infinity, and here also Ts2 is greater than T infinity, but not that much. Okay, so in this case and this case, we cannot actually take the lumped heat transfer approach. Okay, because there is a temperature gradient, and when there is a temperature gradient, there will be spatial variation, and then when the spatial variation is there, we cannot neglect this term d square T over dx square plus d square T over dy square plus and d square T over dz square. This cannot be neglected if you have a spatial variation. Now here, for the second and third case, that is Bi equal to 1 and Bi is much greater than 1, this spatial variation may be in one direction. In this case only x direction is given. Now these two are not there, but still the spatial variation is there. Now when the spatial variation is present, we cannot neglect the energy equation or heat equation. We could have neglected that if the temperature gradient in the x direction is very small. Okay, so in the Fourier law, if dt over dx is very small, dt over dx is small, negligible, then in that case lumped heat transfer approach could have been used. Okay, so that was the first approach in unsteady state heat transfer. So I'll just give the heading for that. Okay, so that is unsteady state heat transfer approach, the third thing of the unsteady state heat transfer approach. And okay, thank you.